Hey guys, good morning all. Just give me a yes in the chat if you guys can hear me and see the sublime text. Quickly give me a yes in the chat if all of you can hear me well and see the sublime text. All of you guys can. Cool. Let's quickly start with session today. We are going to start with graphs today and we'll hopefully finish it by tomorrow. I received the information that tomorrow there's a class schedule. I don't know like for what time exactly. As I can see on my schedule, it's for 4 hours. And tomorrow is national holiday as well, so we'll try to limit it what we can do for the classes. But let's try to finish what we can do for the graphs so we don't have to extend for the next week. But in case, we should not be rushing it. Whatever we can cover, we'll cover it in that part. Okay. Anyways, have a quick revision what you have done till last class before we start with today's session. So in the last class, we have completed about trees and binary search trees and binary trees question. Let's have a quick revision what we did with. We start with question number 13, which is lead code 110 balanced binary tree, right? The question was straightforward. What we need to talk about balanced binary tree is we have to make sure that for each and every subtree, the difference between the left height and the right height should be less than 1. Less than or equal to 1. If it is greater than 1, then it is false. So basically, I need to recur to each and every node. The moment difference becomes greater than 1, then I'm marking the result as false. Otherwise, I'm marking the result as true by default. Time complexity big of n, space complexity big of n. Then we talked about question number 14, minimum absolute difference in BST. This is a good question. You're given a BST, you need to find out the minimum absolute difference. Now, in terms of minimum absolute difference, obviously we know that in a BST, there cannot be duplicate. So minimum absolute difference cannot be 0, but the minimum difference that can happen is at least 1 because we're talking about absolute difference here, right? So no negative values. If I do in order traversal of BST, I will get a sorted list of values. So if I talk about minimum absolute difference, that should be between the adjacent values. And if I talk about maximum absolute difference, that should be between first and last values. So if adjacent value difference is required, then I can take current value minus previous value. I don't need to store the difference. But if first and last value difference is required, that is when I need to store the difference. Okay. That I cannot do it by a single variable. So in terms of approach, I have to do in order traversal, I need to find the difference of adjacent values and minimum absolute value difference. That will be my output. One edge case that you take care of is rather than initializing with just 0, you have to compare with greater than equal to 0. In case 0 is present as one of the elements. Okay, that was only edge case. Time complexity big of n, space complexity big of n, it passed all test cases. Then you move to question number 15, which is lead code 700, which is search in a binary search tree. What is that question? You're given a BST, you're given a number, you need to find search in a binary search tree. You don't have to return a number, you don't have to return a boolean, you have to return that subtree which is rooted there. That's why we're turning a tree node here. Now, since it's a binary search tree, how are we going to search? We are going to search based upon binary search, like this way. This is iterative version, time complexity big of log n, space complexity big of 1. This is recursive version, time complexity again, log of n, space complexity big of 1. Then you move to question number 6 is question number 16, which is lead code 938, which is range sum of VST. It's a good question too. What you're given is you're given a range which is low and high. Any value which is between the range of low and high, both inclusive, you need to calculate their sum. So what I need to do? A binary tree is just a combination of three things. It's a left subtree, right subtree, and the root. So anything which comes between low and high, I will take its sum and will give the answer. Time comes to big of n, space comes to big of n. Then finally move to question number 17. I think this was the last question that we discussed. This has been asked in Google. The question is zigzag level order traversal. What does that question means? You're given the root of a binary tree, return the zigzag level order traversal of its node values. Now, what do you mean by zigzag? So at one level, you will traverse from left to right, another travel right to left, again left to right, and so on and so forth. So alternate between. Now, this is an important one. First, if we are talking about level order traversal in general, that will be a list of lists or vector of vector or 2D array. Why? Because for each level, you will get left to right, then you will get right to left, and so on and so forth. So final answer will be list of list. And the ways when we talk about number one, if I can compare based upon whether it's an even level or an odd level. If it's an even level, I can do left to right. If it's odd level, I can do right to left. So I can keep it count level. This I can code in any language. This logic will work fine for any language. Then the second solution is a Python specific solution. How did we think about this Python specific solution? Because we know a property of list in Python that if I put -1 here, it will give me the output in reverse. If I do +1 here, it will give the output in a non-reverse or the exact format. And we know basic maths property that if I multiply -1 multiple number of times, the output can be even. So if it is even time, the output can be 1, or if it is odd time, the output can be -1. So this becomes the root, or this becomes the root cause for how actually I'm going to implement this Python specific solution. So after every level, I'll multiply this by -1. So this is what we wrote it in the code in Python. What I'm doing is while my queue is not empty, I'm going to each and every level. Now, first I go to left, then I go to right. So by this moment, I have left to right. At the end, I am multiplying it by -1. So if you multiply one time -1, it will become reverse. Alternate, it will become reverse. Again, multiply -1, it will remain same. So alternate time, it will keep on reversing. Time constant big of n, space constant big of n. Then the second solution, which we talked about earlier, which is a generic solution, you can keep a count, and based upon count, you can check whether the modulus is 0 or not. So if that level, this is the current part that I'm storing for a level node list, I got the value in the level node list, then what I'm checking? I'm checking if the level is even or odd. If the level is not even, in that case, I'm reversing it if the level is odd. Okay. Otherwise, I'm just adding to a level node list. Time constant big of n, space constant big of n, passed all test cases. And that marks the end of our trees. Today, what we are going to start with, we are going to start with our last topic for data structure algorithm per se, or the last data structure that we are going to learn about, that is what we call as graph. First, I'll give you the brief about what graph is and what kind of a structure that we are looking at in terms of theory that we have to cover and questions we have to cover. And then we'll move on to the next part. But before that, everybody crystal clear with the revision so far? Any doubts, any questions, please let me know. Come on guys, quickly in the chat. If everybody is clear, quickly type clear in the chat. A revision for trees, everything good? Okay. Everything is good. Let's get started with graphs in that case. Now, when we talk about graphs, it's covered into two parts. There is a basic, which is 70% in terms of content, and there is advanced, which is 30% in terms of content. Basic includes the theory, applications, representations, very important. In representation, we have two kinds of representation, adjacency matrix and adjacency list. Then we have BFS, we have detect cycle in a graph, we have BFS in disconnected graph, and then we have DFS. In terms of advance, what do we have in advance? Advance, we have spanning trees, we have MST, pyramid Kruskal, then we have shortest distance, which includes Dijkstra, Bellman-Ford, and Floyd-Warshall. This thing. Okay. This is what we have in the graphs. So what we'll try to do cover today, we'll try to finish all of this if we can, and then we can think for this tomorrow. Otherwise, we have anyways, if as I can see, it's a 4-hour session, we should be able to do. So we'll start with the theory of graphs, then we'll talk about its application. Representation is very important, understanding adjacency matrix versus adjacency list, then going for BFS, DFS, and so on and so forth. However, the content is more in the basic part and the content is less in the advanced part, but majority of the questions are asked from the advanced part. Obviously, BFS, DFS are the basics of a graph. Without that, you cannot do anything in a graph. But majority of the questions that you will find related to graph will either be directly solved asked upon BFS, DFS, or it will be asked upon the shortest distance kind of things. Okay. That is what your syllabus of graph is. Now let's start with graphs. As I mentioned, as part of every data structure and algorithm we have learned so far, if we want to become master in any DS or algo, know three things about the DS or algo. What are those three things? What, why, and how. What is the use case or the problem statement that DS or algo is solving? What are its applications and how it is coded or implemented? And that's it. Okay. Let's start with number one, which is what. What exactly is a graph? Let's talk about that first. When we define graph, what exactly is a graph? A graph is a finite set of vertices and edges which connects a pair of vertices. A graph is a finite set of vertices and edges which connects a pair of vertices. Okay, let's put it that way. Let's quickly make a graph. 1, 2, we'll just make it here. 3, and then connected with 4. Now observe the keywords that I've highlighted here. Finite, vertices, and edges. Number one, finite means something which is countable, something which is not infinite. So one thing is clear. If something has infinite number of vertices or infinite number of edges, that will not come under the definition of graph. Graph means it is countable number of vertex and countable number of edges. Now, what are these terms, vertices and edges? What do we mean by that? When we say vertices, we are talking about nodes in a graph. And when we say edges, we are talking about connections that connects the vertices. Okay. So in terms of these vertices, that is going to be nodes. Those are going to be 0, 1, 2, 3, 4. These are my vertices. Vertices means nodes in a graph. So 0, 1, 2, 3, 4, those are my nodes. And edges means the connection that connects the vertices. So you guys tell me, what are the edges here? What are the edges here exactly? Come on guys, quickly in the chat. What would be the edges in this graph that we have listed so far? Correct. Edges are just the connection that we are having here. So this includes 0 to 1, 1 to 2, 0 to 3, 3 to 4, and 1 to 4. These are our edges. Okay. So coming back to the definition, a graph is a finite means countable, set of vertices and edges which connects a pair of vertices. Edges are the one which connects a pair of vertices. So I would have something called vertex, or which we call as node in a graph, multiple vertices that we call as nodes in a graph. And I would have edges. These are the connection that will connect the vertices. So if you look at this, my vertices include this 0, 1, 2, 3, 4, and my edges include this, all these 5 edges that I can see here. For 5 vertex, 5 edges. Vertices are represented by V, edges are represented by E. Complexity of graph, when I'll go to the algorithm, that is also presented in forms of V and E. We don't call it n square, n cube, or big of n or something. We always represent in V and E. V means vertex, E means edges. Everybody crystal clear so far? Come on guys, quickly in the chat. All good? Cool. Now, move to the next part is, after we are done with the basic definition of graph, let's talk about types or classification. How we can classify the graph or how we can categorize the graph in general. There are two major ways. One is based upon weight, other is based upon direction. We'll see both one by one. When we say based upon weight, there are two categories possible. Either it can be a weighted graph or it can be an unweighted graph. What do you mean by weighted graph? Weighted graph means there is a weight or a cost associated with every edge in the graph. Okay. There is a weight or a cost associated with every edge in the graph. What do you mean by that? Let's take an example. With every edge, I would like to make a edge. With every edge, I'll make a weight here. So let's say 10, 15. Put this guy as 20. Put this one as 7. Put this one as 5. Okay. One more thing, guys. The weight can be anything. The weight can be positive. The weight can be negative. The weight can be 0. But it cannot be null here. Okay. In case of a weighted graph, there is a weight or there is a cost which is associated with every edge in the graph. This word every is important. When we say unweighted, it means there is no weight or cost associated with any edge in the graph. So there is no weight or cost associated with any edge in the graph. Like if you look at this graph, with any edge, there is no weight associated for it. Okay. Now, tell me something. If I have a graph which has a combination of weight associated with few edge and weight not associated with few edge, which one will you call that? Weighted or unweighted? For example, if I remove 10 from here and if I remove 7 from here, will this be a weighted graph or will this be an unweighted graph? Come on, guess quickly in the chat. Now, will this graph qualify as a weighted or it will qualify as unweighted? Anybody else? Cool. That is the correct answer. See, in that case, neither it will be weighted nor it will be unweighted. The reason for that is you cannot have these values as null. Why you cannot have a null? Think about when you'll be writing the code. Once you go to the code, you'll be doing something like this, u, v, comma, w. So you cannot make this u, v, w null for a particular edge and not for all the edge because all edge will be following the same structure eventually in the code, right? So you cannot do like I can take edge and I can make the value as null. Null is not possible. You can have it zero, you can have it positive, you can have it negative, you can have whatever you want. But you cannot have it null for specific edge and not null for other edges. That is not possible. It should be consistent. Same here. So it will not be a graph altogether. Forget about weighted or unweighted. That is the first classification. We do it based upon weight. If there is a weight or cost associated with every edge in the graph, that is called a weighted graph. If there is no weight or cost associated with any edge in the graph, we call that as unweighted graph. Simple. Second category is based upon direction. So in case of direction, we have again two categories. One is called directed graph. Other is called undirected graph. Directed graph means it's one way and undirected graph means it's two way. Okay, let's talk about this in detail. Can't we take it zero as weight? Weight is not given. No, until unless, see, zero is fine, but we don't assume it if it is zero. If it is null, that's the case I mentioned about. If with any edge there is no weight associated, we cannot assume it as zero. Okay, you can mention it zero, but we cannot assume it as zero. All right, now coming to this. In case of based upon direction, we have two categories. Directed graph, which is one way, and directed graph, which is two way. Take an example. If I say A to B, what does this arrow denotes to me? This arrow denotes that A to B, there is a path. So this is a directed graph, which is unidirectional graph. Okay. Then we have A to B. So we have A to B path and B to A path. How do we know that we have A to B and B to A? Because there is no arrow marked as here, right? There is no arrow which is pointing you have to go from A to B or B to A. So this is what you call as undirected graph. There is no direction, there is no arrow, there is nothing. This is undirected graph. And if you say A to B like this means there is A to B path and there is B to A path. This is not undirected. This is what we call as bidirectional graph. Okay, this is what you call as bidirectional graph. So first one, it's a directed graph or which we call as unidirectional graph. Second one, this is undirected graph. And third one is a bidirectional graph. Bidirectional graph and undirected graph pretty much works the same way. And even if you look at their code, that is also pretty much the same way. Because bidirectional, we are just connecting two edges. Undirected, we are not connecting any edge altogether. Okay. Let me mention that in the comment as well. Bidirectional graphs behave like undirected graphs. Okay. Bidirectional graphs behave like undirected graphs. So the graph that we have been studying so far, let's define what kind of graph that is. This graph is undirected and unweighted graph. There is no weight associated with each and every edge, and obviously there is no direction. So this is undirected and unweighted graph. Everybody crystal clear with the classification. Let me quickly revise. In classification, we have two classification. Based upon weight, you can divide weighted and unweighted. Based upon direction, you can divide it directed or undirected. So for combination, weighted undirected, and unweighted directed and unweighted undirected. Okay. Everybody crystal clear with the theory of graph. Like what is the graph exactly? Come on guys, quickly in the chat. So in definition of graph, we talked about finite set of vertices and edges which connect pair of vertices. We talked about what are vertices, what are edges, what are the classification based upon weight, what are the classification based upon direction. Okay. Now we'll talk about the applications part. The why part or the applications part. What are the applications of graphs? Number one, this is navigation services. For example, any kind of GPS that you are using, irrespective you are using Google Maps or Apple Maps, pretty much all of them are using it already. Okay, let's try to make this guy. Let's take this. Let's see how it works. Okay, now imagine the source here is 0. The destination here is 4. Okay, now these are the cities which are the vertex which are denoting. So 0 can be considered as one city, as one vertex, and 4 vertex can be considered as to be another city. Now you have to go from 0 to 4. So if I talk about all paths from 0 to 4, and imagine these numbers 10, 15, 5, 27, which are the edge weight, these are the number of hours it takes to go from one city to another city. Now, if I have to go from 0 to 4, 0 to 4, what are the ways that I have? One way, I can go from 0 to 1 to 3. No, 0 to 1 to 4. Another way is I can go from 0 to 3 to 4. Is there any other third way? Is there any other third way? There's no other third way. These are the only two ways. So if I go from 0 to 1 to 4, my cost will be 10 plus 20 hours, that will be 30 hours. And if I go from 0 to 3 to 4, that will be 5 plus 7 hours, that will be 12 hours. So what does Google Map or any kind of navigation service done? It calculates from your source to destination whatever the valid path possible. You would have seen it, right? Whenever you use Google Map, you put your destination and then it will find you the shortest path which is available. And sometimes if you're connected by a multiple route, it will list you all the routes. For example, if you go by this car, it will take this much time. If you go by bicycle, this will take this much time. If you go by let's say a train or a flight, whatever that, it will list you all the time. So it will predict you whatever is the shortest path first. So let's say 0, 1 to 4 or 0 to 3 to 4, and it will tell you in the answer whatever the shortest path possible. This part clear to all? This part clear to all? So this is how your graphs are used in the navigation services, the first use case. Second use case or second applications, it is networks and topology in computer networking. So example, I can just give one example. Let's say there are 10 servers. In the 10 servers, you need to connect via star topology, let's say, with minimum cable length. So you got 10 servers, you need to connect in star topology with minimum cable length. So these vertex or nodes that we have, these are our servers. And these edges that we have, these are our cables. Okay. Now, if I have to convert this question into a graph kind of question, I give 10 servers, I need to connect with star topology, I need to use minimum cable length. I can compare those servers are nothing, these are just vertices of my graph, and those edges are nothing, or those cables are nothing, those are just edges of my graph. So my question becomes a graph with 10 vertices, I need to return minimum length connecting all the vertices. All agree? Yes or no? All agree? Yes or no? This is what you can convert the network and topology questions into a graph question and so on and so forth. That is second application. Third application, which you guys have been using for quite a long time, and probably you guys would know about that as well, which is in social media and recommendation system. So any kind of social media, you can take an example, be it Instagram, Facebook, or Snapchat, whatever that is. There are multiple ways graphs are used here. There's not just one way it is utilized, it is utilized in multiple ways. Let's take first example, direction. Is this a directed graph or undirected graph? Let's start with this. Is this a directed graph or undirected graph? Come on, guys, look at the arrows properly. I have three vertices. How many edges I have? Guys, look at the graph carefully. How many edges I have? Okay. Anybody else? Observe it carefully, guys. I have three vertices, which is A, B, and C. And I have three edges, A to B, B to A, and C to B. Observe it carefully. A to B, there is one edge, which is denoting the path here, denoting the arrow here. B to A, there is another edge, which is denoting the arrow here. And then C to B, there is another edge. I have three vertices and three edges. This is a directed graph. Everybody clear? I have three vertices and three edges. This is completely a directed graph. Everyone agrees with this. Okay. Now, why did I take this example? Why did I take this graph? Because I want to show you something. So let's say A can be a person or a page or account, which is my node or vertex. And this edge denotes follows. Okay. Directed in unidirectional, right? Yes. See, whenever we say directed, it means unidirectional. Okay. Whenever if okay, understand. When we say bidirectional also, bidirectional means there are two arrows, A to B and B to A. That's it. Okay. All right. Now coming back to this, why did I take this example? Consider this vertex as the nodes or vertex as a person or a page, and this edge as a follows. So what does that mean? It means A follows B, B follows A, and C follows B. All agree with this part? A follows B, B follows A, C follows B. But B does not follow back C because there is no edge connecting from B to C. Agree? B does not follow C because there is no edge connecting from B to C. And this is something that you would have understood which social media I'm referring about. See, when we talk about Instagram, A can follow B. Is it mandatory that B has to follow back A? Is it mandatory that B has to follow back A? It is not mandatory. B may or may not follow back A. That is what you call as directed graph. But in Facebook, if A and B are connected, means both will follow each other. By default, when two people get connected, they follow each other. This is undirected graph. This part clear to all? First example, in social media, how graph is utilized. It's utilized based upon finding the mapping. What does that mapping denotes? Mapping denotes who is following whom. In case of Facebook, it's undirected graph. In case of Instagram, that is a directed graph. Everybody crystal clear with this? Okay. That is number one. Number two, second use case in social media itself. That is connectivity. What do you mean by connectivity? Let's talk about. I will take the same graph, A, B, and C. Now, look at this. There used to be a word called mutual friends if you have used Facebook before 2018. Not 2018, I think it was 2021 or something. Have you heard of this word called mutual friends? Now, if you use Facebook, there is nothing called mutual friends. Now it will say suggested friends. Okay. They just rename it to suggested friends. Now, what does mutual friends denote? If A will visit profile of C. Is A connected with C? Is A connected with C or is C connected with A? No. A and C are not connected. But when A will visit the profile of C, it will show that they have a mutual connection, and that is B. Agree? Mutual friends or also followed by or whoever, whatever that platform is, it will show you that when A and C are not connected, but based upon the connectivity, it can tell you that if you have any common friends in mutual. Agree? This is the second use case, which is for connectivity. So you create a mapping in the sense you just go over the vertex and you check if there is any common vertex which is common between you two. So you go to all the edges and compare if there's any common vertex, and that's how you can suggest the mutual friends. Last and the important use case, which is personalization slash degree of connectivity. Okay. What is that degree of connectivity? Let's take the same graph. Let's make it weighted now. Okay. Whatever return this weights 110, those weights are closeness score. What do you mean by closeness score? Closeness score means the closeness of connectivity between users. Okay. So when you say closeness score, that means the closeness of connectivity between the users. So I have A, B, and C. What does that closeness of connectivity between users mean? Let's try to understand that. If you're connected with 1,000 people, let's say on Instagram, are you equally connected with all the 1,000 people? Come on, guys, quickly in the chat. You are not equally connected with all 1,000 people. You will be connected with top 5, 10, 20, 100, whatever that number of people for you. How do you determine that closeness score? That score is determined by multiple interaction. For example, in terms of your likes, in terms of your comments, in terms of your messages, in terms of your calls, liking the story or putting or tagging in the story, all of that is used to contribute to your closeness score. Why this closeness score is important? Let's understand that. That closeness score tells about who are your really close friends, right? Or really close connection that you like to communicate with. Why is that important to know about a user is you are most likely to see and engage with their post rather than seeing with some other person post. So here it is. If I have B, right? B I have A and B have C. B has a closeness score of 100 with A and B has a closeness score of 10 with C. So if I show B a post of A and C, with whose post B is more likely to be inclined with? Think about it, guys. If B has a closeness score of 100 with A and 10 with C, if I show the content of A and C both to B, who will B will engage more? Obviously, B will engage more with content of A. So if you want to show both A and C post to B, B is more likely to engage with A post. Okay. Repeating it again. So if this is what the purpose of personalization or degree of connectivity, that helps us understand what person has the highest level of connectivity with what kind of content, what kind of people, and we can push the feed accordingly so the person can be more engaged. The goal of any social media is to increase the user engagement. Everybody clear with this? Okay. Now we move to the next part, which is the how part. How it is coded and how it is implemented. Okay, let's talk about the how part. Now, first thing, we'll talk about the representations and why this representation is important. I'm coming to this part. We have two kind of representation. One is adjacency matrix. Another is adjacency list. Okay. First thing, what do you mean by representation? And then we'll talk about adjacency matrix and adjacency list. Representation means any piece of information which, when provided, is sufficient to redraw the graph is called representation. Okay. Let's keep it at the end of the session. You can ask it for sure, but let's keep it at the end of the session. Let's continue with the graphs that we have now. At the end of the session, just remind me, you can ask whatever you want. Okay. All right. Now coming to representation. There are two kind of representation, adjacency matrix and adjacency list, the way we represent a graph. And before we even go adjacency matrix, adjacency list, let's talk about what do you mean by representation. Representation means if I give you some amount of information or some piece of information, and that piece of information is sufficient that you can redraw the entire graph from it, that is what you can claim it is a representation. Okay, repeating myself. If I give you any piece of information, based upon that piece of information, if it is sufficient to redraw the entire graph, that is when you know that this is called as the representation. Okay, now we have two representations. Let's go one by one. The first one is adjacency matrix. So as you talk about matrix, obviously it's going to have number of rows, number of columns. So V number of rows, V number of columns, it will become V square. Number of rows are V, number of columns are V, so on and so forth. Okay. Now, if a direct path exists, the value will be equal to 1. Else, the value will be equal to 0. Okay. That's the whole purpose of adjacency matrix. Adjacency matrix denotes in that matrix, the value will be 0 or 1, which is binary. If a direct path exists, the value will be equal to 1, otherwise the value will be equal to 0. Let's try to take our graph that we had so far and try to make the adjacency matrix out of it. So this is your graph. How many vertex? Quickly in the chat. How many vertices? 5. So what will be the dimension of the matrix? V cross V means 5 cross 5. This is what my matrix will look like. So let's make matrix. I put a destination here. I'll put the source here. So 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. How do we calculate it? We just mentioned if there is a direct path exists, you put the value equal to 1, otherwise you put the value 0. Now come back to here. 0 to 0, is there a direct path? 0 to 0, is it a self edge on a vertex? No, so the output becomes 0 here. 0 to 1, is there a direct path? Yes, output becomes 1 here. 0 to 2, is there a direct path? No, output becomes 0 here. 0 to 3 direct path, yes, output becomes 1 here. 0 to 4, no direct path, output becomes 0 here. So for the first line or the first row in the matrix, it will be 0, 1, 0, 1, 0. Everybody clear with this? How are we populating the adjacency matrix for a graph? You have a source, you have a destination. Source, we write in terms of rows. Destination, we write in terms of column. If there's a direct path from source to destination, you put the value 1. If there is no direct path, you put the value 0. All clear with this? Okay. If everybody is clear, I want you to complete this matrix. There's a reason I want you to complete this matrix, but anyways, let's complete this matrix. So I've done it for the vertex 0. I want you guys to do it for 1, 2, 3, and 4 as a source to all the destination. Once you guys are done, just mention in the chat. Okay. Quickly finish this matrix and let me know what will be the output of this line, this line, this line, and this line, these 4 lines. There's a reason I'm asking you to do it. So let's do it real quick and then we can take it from there. Come on, guys, 30 seconds should be sufficient for this. Your time starts now. I'm asking you a reason to do that. Complete the matrix altogether so it becomes easier for me to understand it. Quickly in the chat, guys. Yeah, you can message to everyone. All right, guys, enough time. Shall we discuss? I think I got a couple of answers. Let's finalize it real quick. There's a reason I have taken this matrix and I've asked you to do it. So the answer is for 1, it will be 1, 0, then what? 1, 0, and 1. For 2, it will be 0, 1. What else? This is 0, this is 0, this is 0. For 3, it would be 1, 0, 0, 0, and 1. And finally, for 4, it will be, what will be? 0, then 4 to 1, 1. This is 0, this is 1, and this is 0. Okay, this is what we have. Now, let's take this matrix out. I asked for a particular reason why I'm taking this matrix and why I'm asking to complete this matrix. I'll remove this because this is the source. All right. Now you got this matrix out. Can you guys observe something special about this matrix? There are very important things about this matrix. Can you guys observe something special? Think about this matrix and then I can answer. There is something very special about this matrix. I can give this matrix in the chat if you guys need time to analyze. But think about this matrix. There is something very special and there's a reason why it is special as well. Okay, that's one good observation. Diagonals are 0, which is good. Diagonals are 0. Anything else? That's a good observation. Diagonals are 0. Anything else? Think about it maybe. Mirror image. Mirror image. Transpose is same. Okay, cool. First and first column are same and so on and so forth. Adjacency of 1, 0. Okay. Because there are two things that we have observed. Let's go one by one. First, diagonals are 0. What do you mean by diagonals are 0? Diagonals are 0. Diagonals are 0 means adjacency of I comma I, because diagonal would be I comma I. That is 0. If adjacency of I comma I is 0 means there is no self edge on any vertex. All agree? If adjacency of I comma I is 0 means there is no self edge on any vertex. Everyone agrees with this. Come on guys, be quick. That is what diagonals being 0 means. Number 2, if you look at this, if I take the primary diagonal here and I cut across the primary diagonal, you will see this will overlap with this will overlap with this will overlap with this will overlap with this, and this will overlap with this. So if I make a cut across primary diagonal, this left half and this right half will overlap with each other. That is what you call as symmetric. Symmetric across primary diagonal. Agree? All agree? You can verify yourself if it is symmetric or not. Okay. Now the question becomes, why is it symmetric? Is there something special here that we have not noticed? Why is it symmetric? Correct. See, what kind of graph it was? What kind of graph it was? It was undirected graph. Undirected graph means if you will have edge from A to B, that also means you will have edge from B to A. And that is what adjacency representation is doing right now. So an adjacency matrix, any undirected graph, it will always and always will be symmetric across primary diagonal. Why? Because it's a Why? Because it's an undirected graph. So undirected graph, if you say there's edge from A to B, that also means there's going to be edge from B to A. So when you make a entry from source to destination, it also means there will be entry from destination to source. And that's why it is symmetric across primary diagonal. Everybody crystal clear with this? Everybody crystal clear with this? Okay. Now coming to the complexity part. Complexity, since it's a matrix, complexity will be big of B square. Okay, V cross V, which is big of V square. Representation number 1, first of all, representation we talked about any piece of information which is sufficient to redraw the graph. Then we talked about case number 1 or the first representation, adjacency matrix. So V number of vertices will be the matrix will be V cross V, V number of rows, V number of columns. If direct path exists, you put the value 1, otherwise you put the value 0. Okay. We observe two things. If diagonals are 0, means there is no self-edge on any vertex, and for undirected graph, the adjacency matrix will always be symmetric across primary diagonal. Everybody crystal clear with the representation 1? Come on guys, quickly in the chat. Everybody crystal clear with representation 1? Okay. Now we are going to talk about important one, which is case number 2, adjacency list. Will diagonal be always left to right? No, the primary diagonal is always left to right, right? What I'm talking about is, when we talk about being symmetric, we're talking across this diagonal. This is what we consider as primary diagonal. Okay. If you try to look it from, let me delete this. If you try to look it from this diagonal, so if across this diagonal, this, well, no, this will not be symmetric across this diagonal. If you look at this part and this part, pretty much they are not symmetric. So when we talk about symmetry, we talk about across primary diagonal only. Okay. Or you can say that there will be transpose of each other. You can put it as way. Okay. All right, guys. Now coming back to the adjacency list. This is a good representation and we'll be following this representation only whenever we have to code for graphs. I'll tell you the reason for that as well, by the way. Now, what is adjacency list in general? Adjacency list is an array of list. Okay. And what is the size of the array here? The size of the array is the number of vertices. So let's take a graph. Put it here. If I have to make an adjacency list representation of this graph, let's make adjacency list representation for this graph. So it looks like this. I have a vertex A, and that will be connected with list of directly connected vertices with A. This word is important. A vertex A and a list of directly connected vertices with A. So it will be kind of a map like this. A connected with this, B connected with this, and so on and so forth. Okay. So adjacency list representation looks like a vertex A and the list, which is an array. Or yes, it will look like a map where a vertex A will be connected with a list, which is a list of directly connected vertices with A. Okay. Now coming to this. Think of a map where the key is a vertex and the value is a list of vertices. And those list of vertices are those vertices which are directly connected vertices with A. Let's try to write the adjacency list for this. So I got 0, 1, 2, 3, and 4. 0, 1, 2, 3, and 4. Starting with 0. What are the directly connected vertices with 0? Quickly answer in the chat. Directly connected vertices means you will see a vertex which is direct path from 0. Correct. So directly connected vertices are 1, 3. What are directly connected vertices from 1? Correct. It is 0, 2, and 4. What about 2? For 2, there's only 1. What about 3? Or agree? Correct. It's 0 and 4. What about 4? Correct. It's 1 and 3. Okay. This is what you call as adjacency list representation. For every vertex, you can mention about from that vertex, what is the list of directly connected vertices? Now, also one more thing. Remember, I told you representation, right? Based upon this, you can redraw the graph. If I give you this, every vertex and the list of directly connected vertices, can you redraw this graph? Yes or no? If I give you this piece of information, can you redraw the exact graph like this? Yes, you can redraw it. Similarly, if I give you this piece of information, or precisely this piece of information, can you redraw this graph? Yes or no? Of course you can, right? That's exactly what the representation is. So one representation is the form of matrix, adjacency matrix. One representation is the form of list, which is adjacency list. Now the complexity of adjacency list is big of V. So the pros that we have here is starting from big of V square in the case of adjacency matrix, we have reduced to adjacency list, which is big of V. Okay. This is the advantage. And from a code perspective, we will be always using adjacency list. All the questions that you will see that we are going to use, we're going to use adjacency list only. Okay. Anyways, before I go to the question, everybody clear with adjacency list? Representation of adjacency list? Come on, guys, quickly in the chat. Okay. Everybody good? Let's move to one question here. I talked about the pros that we have the complexity from big O of V square in the case of adjacency matrix reduced to big O of in the case of list. However, there is the one con as well. There is a case where adjacency matrix performs better than adjacency list. This is an interesting edge case. There is a case where adjacency matrix will perform better than adjacency list despite having a complexity of big O of V square. Let me give you a question. If you need to check if direct path exists between source and destination, okay? Think of a use case like you put a map and in that map you put a source, you put a destination. One moment. You put a map and you put a destination. In that map and destination, you need to think about whether there's a path exist or not. Sometimes you will see, I don't know if you have tried this or not, try to extreme corners of the world in Google Maps, it will say there is no path. Okay. Try very to extreme locations, it will say there is no path altogether, right? So imagine such kind of edge cases, such kind of scenarios. You're given a source, you're given a destination. You just need to check if a direct path exists or not. If it exists, return true, otherwise return false. Okay. To your question, for weighted graph, how will we represent the weight? So in this case, rather than writing 0 or 1, we'll just represent with the weight, whether it's positive, negative, whatever that is. Okay. All right. Let's get this graph real quick. How is traversal done for graph? We'll go to the question. To answer your question immediately, there is nothing called route. For traversal, we pick a particular vertex. We start traversal from a vertex. So we decide from where we want to traverse. Okay. So there's always a vertex. For example, if I want to start from 0, I'll call 0 as my starting vertex. So you pick one vertex and then you start from there. Okay. All right. Now coming back to this. The question which I was talking about, where adjacency matrix perform better than adjacency list, think about it. If I put source 1 and destination 4, what is the expected output? Does a direct path exist between 1 to 4? Yes or no? Come on, guys, quickly. The correct output is true. To your question, why the complexity is big of V? See, we'll see in the code as well, but just to tell you why the complexity is big of V, we are only concerned about the size of this matrix, size of the list that we are creating. Okay. Obviously, you would have to go through all of this. That's not something we take into account. When we talk about, we're talking about what's the final list that we have created, which is big of size V. Okay. Now, first test case, the output is true. If I put source as 1 and destination as 3, now what is the output? Is there a direct path from 1 to 3? The output is false. Now listen to the question carefully. You're given a graph, you're given a source and destination. Let's say you can take it as a parameter of a function. You just need to check if a direct path exists between source and destination. If it does, return true, otherwise return false. One thing, you have both the adjacency matrix and the adjacency list with you. I'm repeating my statement. You have both the adjacency matrix and adjacency list with you. You don't have to create them, you already have them. Tell me which one will be more efficient in giving the answer to this question if a direct path exists between source and destination. And when you say more efficient, tell me the complexity, how much complexity adjacency matrix will take, how much complexity adjacency list will take. Okay. I'll give you enough time, guys, but are you clear with the question first? Are you clear with the question first? You are given the adjacency matrix, you're given the adjacency list for this graph. You just need to check if I give you a source and destination, what would be the complexity in both the cases? How much complexity adjacency matrix will take? How much complexity adjacency list will take? And which one is better, of course. Okay. I'll give you time, guys. Question is clear. I see people are giving the answers in the chat. I will open up to you guys 30 seconds. Everyone answers based upon this is a very straightforward. I don't want to spend too much time in it. 30 seconds. Think about it. What will be the complexity in both cases? Then we'll have a discussion. Your time starts now. Quick in the chat, guys. Already has enough time. Shall we discuss the answer? Shall we discuss the answer now? Okay. Cool. Number one, let's talk about solutions. Number one, adjacency matrix. Remember I told you both adjacency matrix and adjacency list are already given to you. So you don't need to count the complexity of creating adjacency matrix or adjacency list. If adjacency matrix is already given, what do I need to check? If there's a direct path from source to destination. So what do I need to do? If adjacency of source to destination is equal to 1. If it is 1, you return true. Else, you return false. Time complexity becomes big of 1. All agree? Come on guys, quickly in the chat. All agree? Okay. Number 2, adjacency list. We already have the adjacency list for this guy. Let's take it here. This is our adjacency list 0, 1, 2, 3, 4. This is how it looks like. Now, if I have to check from 1 to a particular vertex whether it exists or not, let's take 1 to 0 to 4. I've taken this out. Now to check if 1 to 3 or 1 to 4 path exist or not. If I have to check that. So if I'm given a source, I need to check whether 1 to 3 or 1 to 4 path exist or not. What do I need to do? I need to go through all directly connected vertices with 1. All agree with this? If I need to go through all the directly connected vertices with 1, because if I have to check whether 1 to 3 or 1 to 4 path exist or not. This complexity is big of V. Not big of E. We are not going through edges. We are going through vertices. So in worst case, one vertex can be connected to all other vertices, right? So in that case, I will need to travel all the vertices in the list. So my complexity will go big of E. I see a lot of people mention big of E, which is incorrect. I'll go through all the vertices here. Okay. So this is the only case when you're given both the adjacency matrix and adjacency list, and you need to check which particular either adjacency matrix or adjacency list will give you the better solution. In this case, this is the only case where adjacency matrix will perform better if you have to find the direct path from source to destination exist or not. This part crystal clear to all? Come on guys, be quick in the chat. Okay. If this is good, now we are moving to the last part. Or not the last part, now we're moving to the next part, which is the coding part. Okay. Now, coding part is interesting here. So first thing, as I said, we'll be using adjacency list only because of the complexity being big of V. So that's what we'll be using for adjacency list. I'll mention you all the ways how you can code in C++, how you can code in Java, and how you can code in Python. So in C++, we can code in two ways. Either I can use STL or I can create a custom class for graph. Same thing for Java. Either you can use collection framework or you can use a custom class. For Python, you can use a module or you can use a custom class. So both ways are there. So in each of these languages, the default STL or collection framework or module provides some definitions. Otherwise, you can create a custom class for graphs, write the functions and do it. Okay. I would start with Python. And the reason I'm starting with Python is super easy code to understand. And you will go step by step why I'm choosing a particular method to write the code for adjacency list. Okay. And then we'll see the code of C++ or Java. Because if I directly start C++ Java code, I'm pretty sure most of you will not understand. So we'll walk through with small Python code, then we'll try to do it, and eventually then we'll see all the other language code as well. Okay. Instead of storing directly connected vertices with array and adjacency list, we can store instead then the complex to the big of one. That is correct. We can do it, but we cannot change the representation. We store it in a list only. That's why we call it adjacency list. Okay. Anyways, coming back to it. Come back to the part where we talked about adjacency list. Remember, what did I talk about adjacency list? A vertex and a list of directly connected vertices. So this is the kind of structure we are going to make. Agree? One vertex and the list of directly connected vertices with that vertex. So basically, if I think it in terms of a map is a key, the key is a vertex or an integer, and the value is a list of vertices or an array. This part clear to all? The key is an integer and the value is an array. Everybody clear with this part first? Okay. Now, what is the alternative of map in Python? What is the alternative of map in Python? Quickly in the chat, guys. Correct. Dictionary. Let's go to dictionary. Any normal dictionary. Let's open lead code. Let's start writing some code. Let's see. All right, here we are. Let's go to Python. Let's make a normal dictionary. So D of A is 1. D of B is 2. What are we going to print? We're going to print D of A and D of B. Okay. Now coming to this. What do you think will be the output here? Come on guys, quickly in the chat. What do you think will be the output here? Correct. If you print D of A, you're printing the value of A. Like what is the value of in the value where the key is A and what's the value where the key is B? So we know the value will be 1 and 2 respectively. Working fine. Things become interesting when if I give D of C. Now what do you think will happen? Come on guys, quickly in the chat. Now what do you think will happen if I put D of C? Null. Okay. But it won't be null, it will be an error. Why? It says a key error C. Why? Because D of C does not exist, right? That's why it said key error C. So let's take this guy first for a normal dictionary and this error as well. Why I'm doing that? Why I'm trying to print something which does not exist? I will explain this once we are done with this. Okay. Anyways, coming back to this. Once we get the solution, then I'll come back to this. Anyways, one thing is clear, my normal dictionary is not working out. It's not giving me the use case that I need. So that's where we have something called default dictionary. So let's talk about default dictionary. So from collections, I imported default dictionary. Instead of making a normal dictionary, I just make it a default dictionary. And in the default dictionary, I can define whatever value I want to pass. Let's say I write a function, default value, and I can return not present. Okay. And I pass this default value function here. Now have a look what is going to happen. 1 exists, it gives the value 1. A exists, it gives the value 1. B exists, it gives the value 2. C does not exist. If it was a normal dictionary, this would have given me a key error. But this is not a normal dictionary. This is a default dictionary. In the default dictionary, I'm passing the default value here, which is not present. So if C does not exist, rather than giving me a key error, it is telling me that, hey, it is not present. I'll copy this Come back here. This is the case of default dictionary. What does the output look like? Output look like 1, 2, not present. Okay, something like this. Now, the question becomes, can't we pass this function to dictionary? We passed this function to dictionary already. This is what we are doing. We are passing this function to dictionary. Or you're saying, can we pass to the normal function dictionary? No. That's where the purpose of default dictionary comes into picture. Okay. Now, this is when I passed a function to it. Is it mandatory to pass a function? Can I do something like, let's say, instead of passing a function, what if I just keep an empty list, right? Or rather than empty list, if I just keep it, let's say, a list data type. Now what will happen? If I run the code now, A exists, output 1. B exists, output 2. C does not exist, output empty list. Isn't that what I needed? Isn't that what I needed? Yes or no? Okay. Now I'll explain everything, whatever I have done so far. So come back here, put it in the Sublime text. This is what we talked about, default dictionary with list. This is my code. My output is 1, 2, empty list. Why did I do all this? Why did I start with the dictionary, then go to a default dictionary, then do a default dictionary with list? Why did I do that in the first place? I did that because understand, when we talk about adjacency list, we know very clearly the structure of adjacency list is like this. You have a vertex, and vertex is connected with list of directly connected vertices. You have a vertex connected with list of directly connected vertices. So V1 connected like this, V2 connected like this, V3 connected like this, V4 connected like this, and so on and so forth. Okay, something like this. Now the node part here. Initially, when I have not done the traversal, understand this. Initially, when I have not done the traversal, a vertex is not visited. In that case, I would want such kind of structure. One vertex, empty list, second vertex, empty list, third vertex, empty list. If I have not traversed all the directly connected edges of a vertex, initially it will be empty. Now, the problem with a normal dictionary is that will not give me an empty list, it will give me a key error. You guys have seen in the code. Agree? I want this kind of a structure where for each vertex, initially, if I have not done the traversal, I want the output to be empty list, or I want the value to be empty list. All agree with this? Come on, guys, quickly in the chat. I'm telling you the use case why we use the default dictionary in the first place. The only purpose of default dictionary is if I use a normal dictionary, I cannot get this kind of pattern without traversing a particular vertex. I want this kind of pattern without traversing a particular vertex because initially they will be empty. That I'm not able to achieve with the normal dictionary. That's why I kept a default dictionary. Okay. So if any vertex is not visited yet, instead of throwing key error, I need empty list along with it. Okay. Hence, used default dictionary instead of normal dictionary. Everybody clear with this statement first? Everybody crystal clear with this statement first? Okay. The purpose why we use a default dictionary. All right. If this part is clear, that's all that we need for the code part. Now we can go to the code of graph. Anyways, whatever you have seen, that was the code of graph, by the way. But now formally, let's write down the code of graph. I'll clear this. Let's start from here. From collections, we import default dictionary. I will just name this as graph. This line itself has made you a graph, by the way. Line number 3 itself is a graph. I'll just name it as a graph equal to default dictionary. Remove these things, we don't need it. I'll add a function called addEdge. So I'll pass my graph there. I will pass my source. I'll pass my destination. In that graph, I will connect source.append destination. Okay. Now I'll be calling this function addEdge. So let's take the addEdge guy and whatever number of edges you want to add. So let's make a graph first. I would have A, C, B, E, and this guy connected with somewhere here D. Okay. Now look at this graph. How many vertices? Come on, guys, quickly in the chat. How many vertices for this graph? Correct. 5. How many edges? How many edges? 4. Can you guys tell me what is the adjacency list representation of this graph? You have already done it. Quickly tell me in the chat. What is the adjacency list representation of this graph? Come on, guys, quickly in the chat. We talked about the list of adjacency list representation. What will be the adjacency list representation for this graph? Correct. Go one by one. If I talk about A, what is A connected with? Same goes for B. Same goes for C. Same goes for D, so on and so forth. Come on, guys, quickly start giving answers. What is A directly connected with? Correct. C. What is B directly connected with? Correct. C and E. What is C directly connected with? C, guys, C. Correct. It's connected with A, B, and D. What is D directly connected with? Correct. C. What is E directly connected with? B. This is how the output of my adjacency list should look like. All agree? This graph with 5 vertices, 4 edges, this should be the adjacency list output. Okay. I am going to comment this guy. I just commented it. Okay. Now what we're going to do is we are going to add the edges first, whatever edges that we have. So graph, let's add edges one by one. First edge is between A and C. Copy, paste. 4 edges are there. A and C, then we got B and C, then we got B and E, then we got C and D. And now I want to print printing adjacency list. This is bidirectional or undirected graph. Okay, bidirectional undirected graph. What do I need to print? I just need to print the graph. Now, there's one thing pending here. I defined the graph, which is default connection dictionary, which is great, no issues. This function, add edge, this is something I need to revisit. What I'm passing in the add edge, I'm passing a source and destination, means make a edge from A to C B to C, B to E, and C to D. This part clear to all? What I'm doing here? I'm just saying, just make a edge between A to C, B to C, B to E, and C to D. Can you guys tell me what is wrong in this code? Line number 5. What is wrong in this code? Come on, guys. Graph is in front of you. Code is in front of you. Quickly debug it. Correct. See, what is happening here? Understand. You said graph of source dot append destination. Means this was source and source was with some empty list. This was the initial because as part of structure of graph, it will be empty list. I'll just remove this comment also. Now, when you say graph of source dot append destination, means now in that there will be a new value called destination. This part clear? Initially, source as a vertex has an empty list. When you say graph of source dot append destination, now in that empty list, you got one vertex which is directly connected. This part clear to all? Okay. Let's comment this guy. Let's comment this guy. Now coming to this. One thing which was missing here is you connected from source to destination, which is great, but you also have to connect destination to source if you're talking about undirected graph. So graph of destination dot append src. That's it. Okay. This is you go. Let's now try to run the code. Now everything looks good. Let's verify the output, whether we are getting the correct output or not. A is connected with C, correct. C is connected with A, B, and D, correct. B is connected with C and D, correct. E is connected with B, correct. D is connected with C, correct. Am I getting the correct output? Yes or no? Quickly in the chat. Come on, guys, be quick. Am I getting the correct output? Quickly in the chat. I am getting the correct output. Okay. So I'm getting the correct output. Let's take, or let's not take it right now. Let's make it some more changes as well. Okay. This was for the undirected graph. How we can do it for a directed graph? Let's see about that as well. I'll take this. I'll paste it here. Bidirectional graph. And how we can do it for a directed graph. Let's have a look at that as well. So for that, let's first make a directed graph. How we can make it? Let's see. Okay. We'll print the graph here. Anyways, coming to it. How do we do it? Let's talk about that first. First thing, I'll just remove print graph from here, or I'll just comment it. This guy I'll comment. This guy I'll comment. Okay. Now coming to this graph specifically, what are we doing it here? I want to make it directed. So I'll keep the same. A is connected with C, B is connected with C, B is connected with E. So A is connected with C. I'll just make this guy as B, this guy as T. B is connected with E. C is connected with D. And B is connected with what? C. Okay. A with C, B with C, B with E, and C with D. A with C, B with C, B with E, and C with D. Now we got this directed graph. For this directed graph, 1, 2, 3, 4, 5, 5 vertex, 4 edges. Quickly tell me, what is the adjacency list now? What about A? Anything will change with A? Come on, guys, anything will change with A? A will remain with C. What about B? Directly connected vertex with B. Come on, guys, anything will change? Nothing will change. It will remain C and D. What about C? Directly connected vertices with C. From where you can go to C? If you are at C, where you can go? Correct. Only D. Now this will change. So previously, which was A and B, now this will change to only D. Next, for D, where you can go to D? If you are at D, where can you go? You cannot go anywhere, so nothing. Same goes for E, you cannot go anywhere, so nothing. This will be going to be my adjacency list for a directed graph. All agree? Yes or no? For a directed graph, this would be my adjacency list. Let's verify that. And even before we verify that, what change I need to do here? What change I need to do here? Correct. See, if I want an undirected graph, I should not be adding back the destination to source. Only source to destination will be there. Okay. Now let's run the code. Let's see whether we get the correct output or not. So let's have a look. A is connected with C, correct. B is connected with C and E, correct. C is connected with D, correct. D is not connected with anything, that's why empty. E is not connected with anything, that's why empty. Now we have seen the code for both directed and undirected graphs. Everybody is still clear with this? Come on, guys, quickly in the chat. If I just comment this line, which I have already done, it will become directed graph. Simple. Have a look at the code, guys. It's super easy code, nothing too complicated. I'll just walk you over again. Once you've understood how do you create a graph, you create a default dictionary of list. Why do we use a default dictionary? Why do we pass that list? We already discussed. The only thing that you're doing is you're calling a function called addEdge. What you're doing in the addEdge, you're passing the graph, you're passing the source, you're passing the destination. If it's going to be a directed graph, you just add from source to destination. If it is undirected graph or bidirectional graph, you add this line also, which is destination to source. Okay. After that, you just print the graph and that will print your matrix. Adjacency list, it will print it as it is. Super easy, super simple to understand. Any doubts, any questions which is not clear, let me know. Adjacency list representation. Come on, guys, be quick. All good. Let's take this code. Come back to Sublime. This is our code. What about the output? Let's write down the output as well. Both the output that we have got. This is for the bidirectional, undirected. This is for the undirected. Unidirectional or directed graph. Okay. Time complexity, as we discussed, it's big of V here. Number of vertices we have to travel. All right, guys. The next topic is traversal. We'll take the next topic in tomorrow's session. That will resume. So I'll just mention it as DFS, BFS will start with tomorrow. Okay. Now coming back to the quick revision, what we have done so far, and we started with the code of graphs, which is great. So adjacency matrix done, adjacency list done, code of graphs done. Traversal is something which we'll discuss from tomorrow. Okay. Yeah, go ahead. You can ask a question. You can ask a question. What about weighted graph? Weighted graph are easier too. So in terms of weighted graph, we are just going to use, for example, we have, once we are connecting with, one moment. Once we are connecting with, we are passing A comma C. We'll ask one more parameter, which we call as W. Okay. So we'll go through that code, by the way. I'll walk through it. What you're going to do in this case is source.append destination. We'll also do up destination comma weight. This is what will make a weighted graph, nothing else. Okay. But we'll do questions or we'll do the weighted graph, then we'll talk about it. Let me quickly revise and then I can answer your question first. So first pass first, in terms of graphs, we have covered till this part or writing a code of a graph, by the way. And then we have 70% of theory and 30% of advanced. That's what we discussed. So we have talked about this. We have talked about this. We have talked about this. First thing, what is a graph? Graph is a finite set of vertices and edges which connects a pair of vertices. Okay. Vertices are nodes in a graph. Edges are the connection that connects the vertices. Then we did the classification. We can classify based upon two criteria. One is based upon weight, so it will be weighted or unweighted. Or if the based upon direction, it will be one way or two way. So which is called as unidirectional or bidirectional. Bidirectional works pretty much the same way as undirected graphs. Then we talked about the applications. How do we understand in terms of navigation services? How do we do it in networks and topology? How do we do it in social media recommendation? Where we talk about three use cases. One for direction, second for connectivity, third is degree of connectivity. Finally, move to coding and implementation. First, we understood two important representation, adjacency metrics. How do we represent? We talked about it's going to be always going to be symmetric across primary diagonal in the case of undirected graph. Then we moved about adjacency list. How does adjacency list look like? Complexity, so on and so forth. We also talked about one edge case where adjacency metrics perform better than adjacency list, which if a direct path exists between source and destination. Then we finally move to the code part. First, we understood from normal dictionary, we have some limitations. Then we move to default dictionary and then passing it with list. Why did we do all that? We did all that because of the structure that we want for the adjacency list. Okay. Obviously, if any vertex is not visited, I want the empty thing rather than key error. So we write down the code of the graphs, undirectional graph, the undirected graph, as well as bidirectional graph, and we have some got the correct output for adjacency list. Time comes to big of fee. The code works. We have verified for all the cases. Okay. All right, guys. Now let me answer the question in the chat that I have got here. I'll go for interview for Salesforce engineer, and the panelists will only ask the conservative Salesforce and Apex programming language, or the can also a DSA. First, depend upon the role. If the role is based upon of a software engineer with backend or DSA, or not DSA, any software engineer which is not working on these Apex technologies, then they will ask you these questions. Otherwise, they will ask you more on the Salesforce side. Anyways, even if they don't ask you, you should know a bit of Apex programming languages and Salesforce because that's the core of Salesforce. Also plays vital role in the long run when the higher package in Salesforce engineer. See, eventually, irrespective if you're talking about a Salesforce engineer, if you're becoming like an expert, you may not need to know about it. But if you're talking about generically becoming a good software engineer, DSA and system design will always go for longer run. Okay. All right, guys. I have covered everything that I have to cover for this today's session. Everything is clear. Quickly give me clear in the chat. Any doubts, anything which is not clear as part of today's session, please let me know. All good? Everything clear? All right, guys. If everything is clear, yeah, what's about the representation? What's the question? Let me know. Okay. If it is not right now, you can ask it in the tomorrow session. By the way, we have a session tomorrow, and that I think the session is scheduled for 4 hours. That I can see on my calendar is 10 p.m. to 2 a.m. So I think 8:30 a.m. in India to 12:30 p.m. something like that. Obviously, we'll not do directly a 4 hour session. We'll keep a break in between. But I won't want to do it in two different classes. So we can take one class and then we can keep a break whenever we like. Okay. All right, guys. See you guys tomorrow if you guys are joining. And from there, we will just try to finish whatever we can do for graphs. Okay. I don't want to rush things, but let's try if we can do it. If you're not able to do it, then we'll schedule for one more class. Okay. All right, guys. Thanks for joining in and let's catch up tomorrow. We'll continue from there. Thanks for joining in. Have a good day. We'll catch up tomorrow.